welcome to Unit 3 Electrons, Concept 1 Notes. This will be an introduction to electrons. And if you're like, wait, we already were introduced to electrons in Unit 2, you are right. But this is going to be a deeper introduction into a lot of things that we need to know about electrons to move forward with the rest of this unit and the units to come. So that's what this is going to be all about. So first, just a little overview. The reason this matters and the reason that I'm dedicating an entire unit to be about electrons is because chemistry is really all about electrons. I always say as a biology teacher that biology is all about the proteins, and for chemistry, it's all about the electrons. They are essential and foundational to literally everything that you will learn. So this unit really matters. So just a reminder, electrons, which we abbreviate as E negative since they have a negative charge, they are subatomic particles. They make up atoms, just like protons do that have a positive charge and neutrons do, which have a neutral charge. But here's the thing. Even though they are subatomic particles, they don't really behave like particles, which is how Bohr predicted them to act with his orbital model. So if you remember from our last unit, we drew Bohr models to represent the structure of an atom. And I love Bohr models from a two-dimensional standpoint. They really help us to actually see the structure of the atom, but they aren't fully accurate in terms of really representing how electrons behave. So this kind of model, it's just not the best way to depict electrons. It's much better to depict them like this because electrons behave much more like waves than they do like particles. And that's what we're going to look at first today. Now, just a reminder, remember that the atom is held together by forces. Mainly, there's an electromagnetic force, which is attractive between opposite charges, like the positive nucleus and the negative electron cloud. Those are attractive. And then there are repulsive electromagnetic forces between like charges. But there's also a strong nuclear force that holds the nucleus together. Okay, so now you may have thought about this when we talked about this in our last unit, but I want to bring it to light again. So, okay, if there's this electromagnetic force that's attractive between the positive nucleus and the negative electrons in the cloud, why aren't electrons just pulled into the nucleus then due to that attraction from that force? And it's because electrons have insane amounts of energy, and this energy keeps them in constant motion around the nucleus. And the energy of electron can change with radiant energy or light energy, or also known as electromagnetic radiation. Okay, so hopefully these orange words down here are words that you remember hearing when you took physical science. But if not, you need to commit them to memory now that these are all the same thing. Radiant energy, light energy, electromagnetic radiation, electromagnetic waves, light waves, we're all talking about the same thing here. And when an electron absorbs this kind of energy, its energy level can change, and that's how it moves can change. Okay, so this is important. So that's where we can tie in electromagnetic radiation. So this is just a form of energy that has wave-like behavior that electrons do too, and as it travels through space. And there are several types of electromagnetic radiation. There are radio waves, microwaves, infrared waves, visible light, ultraviolet rays, X-rays, and gamma rays. And when we're looking at all of these together, we refer to this as the electromagnetic spectrum. It's just all of those different types of radiant energy that I just mentioned. Now, all of these different types of radiant energy travel as waves, and they do that through empty space at the speed of light, which is a constant. We represent it with the letter C, and it's equal to 3.0 times 10 to the 8th meters per second in a vacuum. Now, if you remember from our first unit, you could hopefully convert this, from scientific notation to standard notation, which would be, it moves at 300 million meters per second. That is very fast. Now, because this is a constant among all types of waves, of these electromagnetic waves, we can see other patterns in how these waves, can be quantified or measured. So we can look at their wavelength, which is represented by this Greek letter lambda. We can look at their frequency and their energy. Now, I want to make a little note here. If you had me for physical science, you know that we represented frequency with that kind of fancy F, is what I always referred to it as. That is the letter that is used to represent frequency in physics. In chemistry, we use a different Greek letter, which is kind of like a fancy V, but when I type it in here, it just looks like a normal V. So I want that to not trip you up because you're going to see that and might think velocity, but we're in chemistry now, and this is going to represent frequency. On my test, I'm going to give you a reference sheet that has these labeled out so you don't forget what the letters represent. I'm not going to expect you to remember that because I just don't want you to get tripped up on something like that. But just know that for chemistry, we're using this letter to represent frequency. Okay, so when we're looking at the spectrum, it's important that you know this in order because we see patterns even that you can maybe see looking at here. So, for instance, on this side of the spectrum, we have the longer wavelengths. On this side, we have the shorter wavelengths, which a wavelength is the distance between two like points on a wave. So you can see how much closer these two peaks are compared to like these two peaks on this side of the spectrum. Okay, differently though, this side has the lower frequency and this side has the higher frequency. This side has the lower energy and this side has the higher energy. So knowing these patterns that we see in the spectrum is really, really important for making predictions about these types of waves. So the velocity or the speed of a wave can be calculated as wavelength times frequency. But like we said, the speed of light, these electromagnetic waves, is always 3.0 times 10 to the 8th meters per second in a vacuum. And so instead, we can rewrite this equation for electromagnetic radiation to be C equals wavelength times frequency. Again, that lambda, it represents wavelength. It's a unit of distance for measuring waves. Now, here's something really important. Oftentimes when you see the wavelength of any of those waves we were just looking at in the spectrum, it's going to be in nanometers because waves are so tiny. But to use this equation, because the speed of light is measured in meters per second, to use this equation, you have to have wavelength in meters. Okay, so that's important. So if you're given a measurement in nanometers, you're going to have to convert it to meters in order to be able to use it in the equation. Frequency is this V. That's just the number of waves that pass a given point in a certain time. It's often measured in hertz, and hertz just equal waves per second. And so because it has that second in there, you're good to typically just plug in your frequency into the equation. And for honors, since you're the ones listening to this, we're going to practice this a little bit in a lab we're doing later in this concept. Okay. Let's talk a little bit more about the relationship between wavelength, frequency, and energy because I kind of showed you some trends. You can kind of see them again in this picture too, but let's talk about these. Wavelength and frequency have an inverse relationship, meaning as one goes up, the other goes down, and vice versa. So as wavelength increases, frequency decreases. But frequency and energy have a direct relationship. So as one goes up, the other goes up, and vice versa. Okay, we are going to pause and practice this now in with just some questions that I think that are going to help you kind of process this a little bit. For the sake of the video, though, we're just going to keep chugging along. All right, so let's talk more about electrons and this electromagnetic spectrum, or the EMS. So first, I want to tell you about the photoelectric effect. This is when electromagnetic radiation, so light, look at this, will strike a metal and then electrons are emitted from it. Now, a little bit of context here. I'm telling you this now because if you're like, why is this being thrown at us out of left field? Because when scientists observed this photoelectric effect, it's what helped them to realize that electrons aren't just waves. Okay, they're not just particles, they're not just waves, you know. If they were just waves, what we would see is that when this would happen, we would continuously be emitting electrons regardless of the frequency when they're striking the surface. But what we saw is that the light had to be a certain frequency for certain metals in order to actually emit electrons. And Max Planck was the first to suggest that because of what we saw here with the photoelectric effect, he said that the packets of energy that get emitted, these electrons, are called quanta or quantum, which is plural for quantum. So a quantum is represented by a capital E. It's the minimum amount of energy that can be gained or lost by an atom. Okay, and so Einstein expanded on what Planck said with this idea of quanta, and he said that electromagnetic radiation, he kind of put it all together. He said all this electromagnetic radiation has a dual wave and particle nature. So The electromagnetic radiation, light, has wave-like properties, but also can be thought of as a stream of particles that are carrying a quantum of energy, an amount of energy. And he called these streams of particles photons. So we're not going to get into crazy detail about all of that, but I do want you to see this equation because it is useful for calculations. So energy, this quantum, this amount of energy, can be calculated as H times frequency. So E represents the energy in a quantum of electromagnetic radiation, and we measure it in joules, which is a unit you hopefully remember from physical science. And then this H is Planck's constant, because remember, he was the guy who first kind of came up with this. And it is 6.626 times 10 to the negative 34th, which is measured in joules per second. And then again, this is represented by frequency, which is measured in hertz. So all of this to say, this is why this matters and why I want you to care about this, is if you know the frequency of, a wavelength of light or of electromagnetic radiation, you can then calculate how much energy there is in it because of this equation. And again, that's something we'll put into practice in a lab in a little bit. Okay, let's bring it back to something a little bit simpler. You remember from last unit that electrons are in the electron cloud and the cloud is divided into shells or energy levels. And electrons exist in specific energy levels based on how much energy they have. And this is considered their ground state. Now, when they absorb energy though, they can then jump to a higher energy level. And when they do that, that is their excited state. And so that's what we can see here in this orange picture. You've got an electron in its ground state. It absorbs electromagnetic radiation and then gets excited and jumps levels. When it releases energy, it's emitted as light, and then it can drop an energy level back to its ground state. So if you were in person with me right now, I would demonstrate this with a ladder. I would place a ladder against the wall of the classroom, and I would tell you, think of the ground as the nucleus of the atom, and think of each rung on the ladder as a different energy level in the electron cloud. The higher up you go on the ladder, the further away you are from the nucleus, and the more energy it's going to require for you to be that far away because you're having to overcome that attractive electromagnetic force between the positive nucleus and your negative electrons. So the more energy an electron has, the further from the nucleus it can be. So picture me just like chilling on the ladder against the wall, and then consider if I got zapped by some sort of light energy and I absorbed that, I would then potentially have enough energy to jump up to the next rung on the ladder, the next energy level further away from the nucleus, and that would be when I'm in my excited state. But as I lose energy, or as it's given off in the form of light, I would then go back down the ladder rungs to be back into my ground state. And so that light that is given off is important because that relates to the emission spectrum, which is the spectrum of light that's released from excited atoms of an element. It's the amount of energy emitted that determines the color of light given off. Because if you remember from what we just calculated, amount of energy is related to frequency. And if I know the frequency, then I know I can figure out the wavelength and where it falls on this. And especially for invisible light, the light that we can see, all these different colors of light have different wavelengths and frequencies and energy levels. So if they have longer wavelengths and lower frequencies and lower energy, they may be more red. And if they have shorter wavelengths and higher frequency and higher energy, they may be more purple. Okay, so we are going to look at this in a lab today, and I think it's going to help you really see this and understand this a lot better. So we're going to do that, but for, again, the sake of the notes, we're going to keep pushing through in our Introduction to Electrons concept. Okay, so now let's talk about, we've talked about electrons and the electromagnetic spectrum and light and color and all of that, but now let's talk about electrons and what they mean for the stability of an atom. Okay, so remember, the nucleus of the atom, which has the protons and neutrons, doesn't change much. It's actually very difficult to change. It will only change a lot if it's radioactive. And even still, that's going to be a nuclear reaction, which we saw in our last unit, is kind of a big deal. It requires an insane amount of energy. But here's the deal. That's the nucleus. Electrons are a different story. Remember, those electrons are constantly moving within the atom, and they can be transferred to form bonds to gain stability in compounds. Now, speaking of that constant motion, This is where I need to bring up the Heisenberg uncertainty principle. Because they're in constant motion, it's really impossible to determine the position and velocity of an electron or other particle simultaneously. We just really can't do that. But we do need to have somewhat of an idea of where electrons are so that we can predict how they will behave and thus the properties of the atom. Okay? And the most important electrons to look at are the valence electrons. So again, this should be a familiar term from last unit, but these are the electrons in the outermost energy level of an atom. We call this the valence shell. All of the other electrons are referred to as the core electrons. Now, for main group elements, remember, when you're looking at your periodic table, we're talking about everything but the transition metals because they kind of do some funky things, which we'll talk more about later in this unit. But remember, for main group elements, the group number represents the number of valence electrons for all the elements in that group. Okay, so for example, all of those elements in group 1, hydrogen, lithium, sodium, potassium, etc., all of them have one valence electron in their outer energy level. All of the elements in group 2 have 2. The elements in group 13 have 3, 14 have 4, 15 have 5, 16 have 6, 17 have 7, okay? So if you remember that. And this number of valence electrons, this is what's determining the behavior of atoms because having the same number of valence electrons gives these elements similar properties. That's why we see fluorine and chlorine and bromine, all those halogens in group 17, they act similarly because they have the same number of valence electrons. Now, this is why this matters for stability. Atoms are most stable when they have full outer energy levels of electrons. And for most atoms, the tendency is for the octet rule, which means a preference for 8 valence electrons. Now, hydrogen and helium are an exception because they only have one energy level. And if you remember that first energy level that's closest to the nucleus, it only holds 2. But pretty much everyone else, we're shooting for 8 here. Now, if you remember, group 18, which is our noble gases, they already have 8 valence electrons, and helium has its 2. So they're already stable because they have full energy levels of electrons. But other atoms want to do this. So they will gain, lose, or share their valence electrons within bonds in order to become stable. So for example, let's look at this Bohr model of sodium, okay? Sodium has 1 valence electron. So in order for it to get 8, it's either going to have to gain 7 electrons or just lose this 1. And then its outermost will be this one, which has 8. Okay, so look at chlorine. Chlorine has 7 valence electrons. It would either have to lose all 7 or just gain 1 to be stable. Well, it makes much more sense for sodium to give away this electron to chlorine, and then they both get 8 and they're both stable. So that's what we will see happen. And this is a bond that forms in the compound sodium chloride, or NaCl, which is table salt. And again, this is just an introduction to this. Our entire next unit is devoted to bonds. But I needed to bring this up now because, again, this is all about the valence electrons, and this unit is all about electrons. Okay, so if you remember, I also introduced you to this term in the last unit. If an atom gains or loses electrons in order to become stable, it then becomes an ion. And ions are just atoms or molecules that have a charge due to having lost or gained electrons. So cations are specifically the positively charged ions. They have lost electrons. And when they lose electrons, that means they have more positive protons than they have negative electrons. Thus, they get this positive charge overall. Typically, we see that cations are metals. Why? Well, look at your periodic table. Remember, pretty much almost the entire left side of the periodic table, those are all metals pretty much. And so they have, 1 valence electron, 2 valence electrons, 3 valence electrons. It's much easier for them to lose 1 or 2 or 3 valence electrons than gain 7, 6, or 5 valence electrons to be stable. So here's an example. Look at magnesium. It has 2 valence electrons, which I highlighted here. So instead of gaining 6, it's just going to lose these 2 in order to be stable. And so that makes it a cation. It will have a positive 2 charge because now it has 12 protons and only 10 electrons. That gives it an overall positive 2 charge. And so we would write this cation as Mg with a plus 2 charge. Okay, on the other side, we have anions. Anions are negatively charged ions that have gained electrons. These are usually nonmetals, okay, because they're making up the right side of the periodic table. And those on the right side of the periodic table, in group 15, they have 5 valency. In 16, they have 6. In 17, they have 7. It makes so much more sense for them to gain 3 or 2 or 1 valence electrons than lose 5 or 6 or 7. So look at oxygen. It has 6 valence electrons. So it's going to make the most sense in order to become stable for it to just gain 2 electrons. And that will make it an anion because then it would have 10 total electrons with only 8 protons, which gives it an overall -2 charge. And we would write it as O with a -2 charge. Now, I love these Bohr models. I think it really, even though they don't accurately depict how electrons behave, they help us just kind of see the atom. But if you notice, we're not even really looking at these core electrons at all. We're really just looking at the valence electrons. And so that's where a different kind of drawing can be a simpler representation of what we need to make predictions about how these atoms are going to act. And that's where we are going to learn about Lewis structures. So a Lewis structure is just a convenient and simple way to represent an element and its valence electrons. Bohr models are just more robust and they take more time, and you don't need that when we're just wanting to look at the valence electrons. And so they look like this. I just want to make a note here too that Lewis structures can be referred to as Lewis dot diagrams or electron dot diagrams. And so just know that all of those terms are interchangeable. Okay, and so this kind of Lewis structure shows us 2 things. It shows us what the element is with the symbol, and then it shows us how many valence E it has, which is helpful for us when we're trying to predict, again, how it will behave, because electrons are the ones that are making a difference here. Okay, so how do we draw these? When you're going to draw them, instead of drawing the whole nucleus like you do for a Bohr model, you're just going to represent the nucleus with an atomic symbol. Okay, so for example, nitrogen. If I was going to draw a Lewis structure for nitrogen, I would literally just draw an N to represent the nucleus. Okay, and then you're going to determine the number of valence electrons from the group number. So look at nitrogen on the periodic table. It's in group 15, so it has 5 valence electrons. Now, we're going to represent those valence electrons by drawing dots around the chemical symbol. But here's the kicker. We're going to fill one side at a time before we pair any electrons up. Now, there's a reason for this, and we'll get into it a little bit more in concept 2, but I just want to give you a heads up on that now. Just follow that rule and you'll be good to go. Okay, so if there's 5 valence electrons, we'll do 1 on the top, 1 on each side, and then we'll start pairing them up from there. So that's where we get our 5 valence electrons. Okay, so now I want you to practice this for hydrogen, carbon, fluorine, and phosphorus. Try drawing those Lewis structures. We'll go over them, and then after that, I want you to do some more practice with that in your packet before we dive a little bit deeper into other things with electrons further into this unit.